Hello friends, welcome back. In this video, we will discuss about VXLAN implementation with BGP EVPN on Arista EOS platform. So we will discuss how VXLAN BGP EVPN works on Arista EOS devices along with the configuration and verification of the same. And we will also discuss how MLAG behaves with Anycast VTEP IPs when working with BGP EVPN. So without further ado, let's crack on. So friends, in our previous video, we discussed why static flood lists fall short when it comes to implementing EVPN on Arista devices and how it has its own limitation when it comes to scalability. And in this video, we will discuss how BGP EVPN helps in overcoming those limitations. And we will discuss the workflow of how tenant VRFs are set up on Arista devices along with the VXLAN tunnel interface with BGP EVPN address family. Then we will discuss how MAC and IP routes plus the IP prefixes get routed over the Arista fabric along with the verification commands, and we will also include MLAG Anycast VTIP behavior in the mix. So yeah, there is a lot to unpack in this video, so I will suggest you to watch this video till the end. And also, if you haven't watched the static flood lists variation of EVPN on Arista platform, I would suggest you to do so before you watch this video. So friends, let's discuss what BGP EVPN adds to VXLAN and what does it offer as compared to the static flood list variation that we discussed in the previous video. So BGP EVPN helps with dynamic learning of the remote VTIPs and also advertise the MAC and IP addresses for devices inside the VLANs that map to VNIs. It also adds a control plane component to VXLAN's data plane forwarding of VXLAN encapsulated traffic. So like we discussed in the static flood list variation of EVPN, anytime we received an ARP request from the source host, we need to advertise that to all the remote VTIPs or all the remote leaves, regardless of whether that particular leaf or VTIP is using that particular VLAN or VNI or not. So with static flood list, what we would do is we would statically configure a list of remote VTIPs, and whenever we receive an ARP packet, for example, from a local host, we will send that ARP request to all the statically configured remote VTIPs, irrespective of whether that particular VTIP is using that VLAN or not. So one of the advantage of BGP EVPN, in addition to dynamically learning the VTIPs, is that we would automatically learn the VLAN to VNI mapping on the remote VTIPs. So like we will see in the configuration section as well, that anytime we configure the VLAN to VNI mapping and add it to the VXLAN tunnel interface, the local VTIP will generate a type 3 route, which is also called inclusive multicast Ethernet tag route to the BGP neighbors, which will be our spines, and those spines will advertise that type 3 route to the other remote VTIPs. So that way, bump replication will stay scoped to only the interested endpoints or the interested VTIPs. And thirdly, with BGP EVPN, we advertise the MAC and IP information with EVPN routes instead of relying on pure data plane flooding. So BGP EVPN is used to advertise MAC address, that is EVPN type 2 routes for layer 2 VXLAN, and also IP addresses, which are the EVPN type 5 routes for layer 3 VXLAN. So if we compare the implementation of BGP EVPN versus static flood list, we can clearly see that with static flood list, the ARP and unknown traffic get replicated to statically configured remote VTIPs, whether they participate in that VNI or not. So the remote leaf definition is manual, so scaling can become a factor when using static flood lists. So it does add an element of operational overhead, but with EVPN-driven head-end replication, bump traffic is only replicated towards the VTEPs that advertise interest in the relevant VNI, and we advertise the interest using EVPN Type 3 route, which are the inclusive multicast Ethernet tag routes. And with BGP EVPN, the host MAC and IP learning is carried in BGP EVPN, which helps in shrinking unnecessary flood domains and gives us a cleaner control plane and a more efficient head-end replication design. So like we will see in the configuration section that even though BGP EVPN has a lot of moving pieces when it comes to configuring it, but once it has been configured, the operation is much cleaner as compared to static flood lists. So if we have a glance at the overlay logic, so if host A needs to communicate with host B, so we have the VLAN to VNI mapping on leaf 1, and leaf 1 will have BGP session to the spines. So in our topology, we will have 3 leaves and 2 spines. So for example, leaf 1 will have a BGP session towards spine 1 and another BGP session towards spine 2 for redundancy. And likewise, leaf 2 and leaf 3 will have the BGP sessions towards the spines. And like we discussed, the spines will act as root reflectors, and all the leaves will have loopback to loopback underlay reachability. So as far as the spines are concerned, its job is to receive VXLAN encapsulated traffic from leaf 1 and forward the traffic towards the destination VTEP or the destination leaf. So in the data plane, the traffic crosses the fabric from leaf loopback to leaf loopback, while EVPN supplies the control plane state used to choose the correct remote VTEP and tenant context. So we will add the relevant route targets and route distinguishers to add the control plane state information to the VXLAN fabric. So once leaf 1 knows about the locally attached host, for example host A, it will advertise that MAC and IP information to the spines. Spines will advertise the MAC and IP information to leaf 2, and assuming that leaf 2 has the same VLAN to VNI mapping configured, and then it will know about host A in control plane, and that happens even before host A has sent any traffic towards host B. And likewise, leaf 2 will learn about host B, and then it will advertise the MAC and IP information of host B towards the spines as BGP EVPN route, and the same will get advertised towards leaf 1. So the learning of MAC and IP information happens using BGP EVPN at the control plane. So the key EVPN routes will remain the same. They are route type 2 and route type 5. So route type 2 being the MAC or MAC plus IP advertisement, and route type 5 being the IP prefix advertisements. So like we have discussed in the previous videos, we use the route type 2 to advertise MAC or MAC and IP information to our BGP EVPN spines, and the route type 5 or to advertise the IP prefix, and that's ideal for routed overlay reachability. So if you're trying to route externally, that's when route type 5 comes into picture. And for the EVPN tenants, we will configure the route distinguishers to make the routes unique per advertising context. And then we will also add the import and export route target per tenant or per VRF to add the control plane element to EVPN. And then under the VXLAN tunnel interface, we will configure VLAN to VNI mapping, and we will also assign a layer 3 VNI per VRF, and that gets used for inter-VLAN routing using the same underlay network. And if we check what are the prerequisites and caveats for EVPN to work on an Arista device, the first thing that we must enable is the service routing multi-agent command, And this is required for the EVPN VXLAN workflow, and this command requires a reload. So this needs to be planned well in advance and ideally in a maintenance window. And also when we configure BGP between the leaf and the spines, we need to exchange or enable extended communities, as EOS does not exchange them by default, pretty much like any other Cisco device where the extended community needs to be explicitly defined. And this is the command that we will enter to exchange the root targets and any extended control plane attributes. And also when we activate the EVPN address family on an existing BGP neighbor, it renegotiates the session and it can disrupt traffic forwarding for other negotiated address family identifiers. So that needs to be scheduled in a maintenance window as well. So these are some of the caveats and some of the prerequisites that needs to be considered before we start implementing or configuring BGP EVPN on Arista devices. And now if we look at the configuration side of BGP EVPN, so once we have enabled the service routing protocol model multi-agent command, and once the device has reloaded, the first step will be to create the tenant VRF. So the command is VRF instance, the VRF name, and then we also need to enable routing because on Arista devices, IP routing is disabled by default until it's explicitly enabled. So the step 2 would be to move the SVIs or the VLAN interfaces into the respective VRF. For example, interface VLAN 10 will be part of VRF, let's say VRF customer A, and then we define the IP address along with the IP virtual router address. That's similar to configuring HSRP on Cisco devices. And this also needs to be planned carefully because assigning the VRF removes the SVI IP and then it needs to be re-added manually. So friends, one of the important elements of this configuration is the IP virtual router address command. So we configure the same virtual MAC address and IP virtual router address pair on all the leaf switches that will be servicing the same VLAN segment. So if a VM needs to be migrated from one segment to another, the VM does not need to update its IP address, its default gateway, or clear its op cache, etc. So we configured the IP virtual router command under the SVI, and that allows multiple active forwarder and all the leaves serving the same VLAN to act as active forwarders. So we configured the same virtual IP and virtual MAC address for first hop routing, and this needs to be configured on all the leaf switches that will be servicing the same VLAN segment. And this also needs a global MAC address configured, and the command that we need to configure the global MAC address is the IP virtual router MAC address command. And then we configure the interface VXLAN command. So this is the tunnel interface that we configure on the leaf switches, and this represents the VTEP to VTEP tunnel. And under the interface VXLAN configuration mode, we define the VXLAN source interface, and usually we use the loopback 0 interface as the source for the VXLAN tunnel. And then we define the VXLAN to VNI mapping. And then we also have to define a VXLAN layer 3 VNI. This will be used for inter VLAN routing, i.e. from VLAN 10 to VLAN 20, for example. And then we establish the BGP pairing between the leaf and the spine devices. And like I mentioned earlier, we must enable the extended community using the send community extended command per neighbor. So these are our example spine devices, and under the address family, we activate those neighbors. So the BGP EVPN neighborship carries the overlay reachability between the peers, and the extended communities carry the root target information used for tenant import and export. Hence, we must enable the exchange of extended community while configuring the BGP peering. And without this step, the EVPN control plane state will not propagate correctly. And then inside the router BGP configuration mode, we define the VLANs that we want to advertise using BGP EVPN. So we define the route distinguisher, the route target, and redistribute the learned routes. And likewise for layer 3 routing, we define the VRF, the route distinguisher, we define the route target import and export statements, and then we also redistribute the connected routes to advertise the layer 3 tenant IP reachability in the VRF using the EVPN IP VRF context. So within the VRF, we redistribute the connected prefixes, and the remote VTAPs can import these prefixes using the import statement. Just to recap the sequence of steps that we went through to configure BGP EVPN. So the first step was to enable the service routing protocols model multi-agent command, which requires a reload. And then we created the tenant VRF, and then we bind the SVR and restore its IP and virtual gateway settings. Then we configured the VXLAN tunnel interface with the loopback 0 interface as the source. We also configured the VLAN to VNI mappings and also the VRF to layer 3 VNI mapping. And then we went to configure BGP between the leaf and the spines. We added the send community extended command as the extended communities do not get exchanged by default. We activated the EVPN address family, and then we configured the redistribution of VLAN and VRF under the EVPN address family. So these are some of the verification commands that we run when we configure BGP EVPN. So the show BGP EVPN summary command helps you to verify the BGP peering between the leaf and spine. We can also check the VXLAN interface with the show interface VXLAN 1 command. Then we have the show VXLAN VTAP command, which shows the remote VTAP discovery. And then we have the show MAC address table command, which helps you to see the local and remote MAC learning. And then we have the show VXLAN address table. Again, it will show the mapping between the learned MAC addresses with their corresponding VTEPs. And then we have the show BGP EVPN command, which shows the learned EVPN routes. And we can use the show BGP EVPN command along with the various route types, which includes the MAC and IP route and also the IP prefix route. So friends, an important thing that we must consider when we are working on an MLAC topology is that for southbound ports that are configured in an MLAC, the MAC addresses of the southbound devices are learned on both the peers in the MLAC pair, which means that the Arista MLAC peers will advertise the MAC address in BGP EVPN. And when they advertise the MAC addresses, they will be advertising the same MAC address in BGP. So if we try to understand this using our topology, so traffic from switch 1 will be load balanced to both Arista 1 and Arista 2, which means the same MAC address will be learned on both of these Aristas. And when these Aristas learn the MAC address from their southbound devices, they will advertise those MAC or MAC and IP routes towards the spines. So we need to make sure that when Arista 1 and Arista 2 advertise these MAC or MAC and IP routes towards the spines, they use the same next hop address. So in order to achieve that, we will configure a new loopback that is an Anycast IP address and advertise that into IGP, and then we will source the VXLAN tunnel interface from that new loopback IP address. So that way, what will happen is that when the remote leaf will receive an update from either Arista 1 or Arista 2 via the spines, they will see the shared next hop address. So for example, if we configure a shared next hop address of 10.0.0.12 on both Arista 1 and Arista 2, the remote Aristas will see this new address as the next hop for any MAC or MAC and IP routes coming from either Arista 1 or Arista 2. That way, the return traffic towards Arista 1 or Arista 2 could be load balanced between these two MLAC peers. If we don't do it, what's going to happen is that the remote leaf, i.e. Arista 3 or Arista 4, will see either 10001 or 10002 in the BGP table, and based on the BGP best path selection, one of these two Aristas in the MLAC pair will always be selected as the next hop, which will lead to traffic polarization. So in order to avoid that, we configure a shared IP address as the VXLAN tunnel source interface on both Arista 1 and Arista 2. However, the BGP source interface will remain the same, i.e. they will use the unique loopback 0 IP address to establish the BGP session with the spines. As for BGP, we need to have the unique addresses to establish the TCP session. So friends, let's now jump into our lab section and configure these Arista devices in a step-by-step manner. So in our topology, Arista 1 and Arista 2 are configured in an MLAC pair. So I have configured the MLAC pairing already to save some time. And then we have Arista 3 and Arista 4. They are standalone Arista devices. And the loopback 0 IPs of these Arista devices are configured as per their device number. So Arista 1 has a loopback 0 IP of 10001, and Arista 2 has an IP of 10002. Arista 3 has a loopback IP of 10003, and Arista 4 has a loopback IP of 10004. We also have two spines, Arista 5 and Arista 6. Arista 5 has a loopback IP of 10005. Arista 6 has a loopback IP of 10006. And like you see on the screen, these Aristas, i.e. Arista 5 and Arista 6, are configured as root reflectors, and these leaf switches will run address family BGP EVPN with the spines. So they will be the root reflector client for the root reflector servers, i.e. Arista 5 and Arista 6. So like we checked in our theory section, the first requirement or prerequisite for configuring BGP EVPN address family is to enable multi-agent model using the command service routing protocols model multi-agent. And if we check this configuration on our Aristas, so let's go show running config section service. We see that we have enabled this command already. So I have this command enabled on all the Aristas, and I have also reloaded the device to save us some time. So let's go on Arista 2 and run the same command. So we have the command enabled. We have the same config on Arista 3, Arista 4, Arista 5, and last but not the least, Arista 6. So our devices meet the first requirement to run BGP EVPN. So let's now configure the VRF instances on all the leaf switches and also enable IP routing for those VRFs. And we need the IP routing command against all the VRFs that we create, because routing inside a customer VRF is disabled unless we enable it explicitly. So let's go to Arista 1. So let's give it a name, VRF instance. So let's call it customer A, and then we enable routing for VRF customer A. So let's say if we undo this command and let's check the VRF. So we see that under VRF there is no routing enabled for IPv4 or IPv6 by default. So this is the default behavior of Arista EOS devices. So let's go back to VRF instance customer A and enable that command, which is IP routing VRF customer A, and let's check the VRF again. So now we see that routing is enabled for IPv4 for VRF customer A. The next step would be to configure or move the SVIs into the respective VRFs. So let's go to Arista 1 again. So from our previous lab for static flood lists, we did create interface VLAN 10, and it is under the default VRF currently. So we will move this to VRF customer A. So let's go interface VLAN 10. Let's give the command VRF customer A, and as soon as we assign this interface to another VRF, it will remove the IP address that has been configured on that SVI. So let's apply the IP address command once again, and also the IP virtual router address command. And like we discussed in the theory section, we need the IP virtual router address to enable Anycast gateway with a virtual ARP. So all leaves that are servicing the same VLAN segment will need to have the IP virtual router address command under the SVI along with the IP virtual router MAC address command, and this will ensure that hosts can keep the same IP gateway and ARP entry irrespective of which leaf switch they are connected to. So let's say if we do a show run section virtual, we see that we have the IP virtual router address command under the SVI, and we also have the IP virtual router MAC address command. This is a global configuration mode command that we configure on all the leaf switches that will be servicing the same VLAN segment. So we configured the VRF on Arista 1 and also enabled routing for that VRF. So let's do the same on Arista 2. So let's say if we do a show run section VRF, let's create the VRF. Let's do IP routing for VRF customer A. If we now check show VRF, we see that customer A has IP routing enabled. So let's go to VLAN 10 and assign this SVI to VRF customer A. We re-add the IP address and also the IP virtual router address under the SVI. So that's done. So we do the same on Arista 3, VRF instance customer A, IP routing, VRF customer A, show run interface VLAN 10, interface VLAN 10, VRF customer A, reapply the IP virtual router. That's done. Let's save the config. Let's do the same on Arista 4. So we say VRF instance customer A, IP routing for VRF customer A, show run interface VLAN 10, interface VLAN 10, VRF customer A, reapply the IP address and the virtual IP. That's done. Save the config. So we created the VRF and moved the SVI VLAN 10 in our topology into the newly created VRF. The next step would be to configure the VXLAN tunnel interface using the interface VXLAN 1 command. So we did configure the interface VXLAN 1 from our previous lab. So we go to interface VXLAN 1 configuration mode. We specify the source interface, which is loopback 0, and then we command VXLAN UDP port 478, and that's the default port that VXLAN uses. So this is a default command, so we don't have to specify the UDP port. And then we define the VXLAN to VNI mapping or VLAN to VNI mapping. And in our topology, we mapped VLAN 10 to VNI 100,010, and then we had specified the static flood lists using the VXLAN flood vtep command. So we will undo this command because we will now be using BGP EVPN to advertise MAC and IP routes and not use static flood list. So we will do no VXLAN flood VTEP command on all the Aristas. So let's go to Arista 2. Let's check the VXLAN 1 interface. So let's undo that command first. So we go interface VXLAN 1, no, that's fine. So let's check the same on Arista 3. So interface VXLAN 1, no flood VTEP on the Arista. Let's go to Arista 4, show run interface VXLAN 1. Okay, so let's go to interface VXLAN 1 and let's undo this command again. Okay, so now we will configure the VXLAN layer 3 VNI. This layer 3 VNI will be used for layer 3 routing between two different segments. So if a host in VLAN 10 needs to communicate with a host in VLAN 20, we will need the routing element between these two hosts as they are in different segments or different VLANs. So let's go to interface VXLAN 1. So the command is VXLAN VRF customer A, and then in our topology, the VNI value we will be using is 100,001. So that will be the same layer 3 VNI on all the other leaf switches as well. So we will go interface VXLAN 1, VXLAN VRF customer A, VNI 100,001. Okay, let's do the same on Arista 3 and on Arista 4. So the next thing that we need to do is configure BGP between the leaves and the spines, and specifically we will enable address family EVPN between the leaves and the spine devices. So let's go to Arista 1. So if we do show run section router, we see that currently we are only running OSPF on any 10.0.0.0/8 network in area 0. So we will now need to enable BGP between the leaves and the spines. So this will be an iBGP pairing where the spines will be serving as route reflectors. So we will go router BGP 100, neighbor 10.0.0.5, remote AS is 100. Likewise, we will run the same command for the other spine, which is Arista 6. And then we will go address family EVPN and activate the neighbor. Then we also need to make sure that we enable send community, as this is disabled by default, and we need the extended communities to exchange the root targets. So we activated the neighborship, and then we also enabled the send community command. And also with this pairing, we will be using our loopback 0 address as the source interface. So the command is neighbor 10.0.0.5 for Arista 5, update source loopback 0. Likewise, we will do the same for Arista 6. And then for Arista 6, we also need to enable the send community extended command. So now if we look at the BGP configuration, we enabled the BGP process using router BGP 100 as our AS number. We configured the neighbors 10.0.0.5 and 10.0.0.6 using the same AS number, which is AS number 100. We used update source loopback 0 as the source interface, and then we enabled the sending of the extended community values for both Arista 5 and Arista 6. And then under address family EVPN, we activated Arista 5 because we need to run address family BGP EVPN between the leaves and the spines. But currently, we only have the command enabled for neighbor 10.0.0.5, which means that we also need to do it for neighbor 10.0.0.6. So let's do that now. Show run section router. So we have the address family EVPN activated for both Arista 5 and Arista 6. So we can use it as a template and apply the same config on all the other leaf switches, i.e. Arista 2, Arista 3, and Arista 4. So now that we have configured BGP config on the leaf switches, let's go to our spines and configure BGP on the spines. So let's say if we do a show run section router, we see that we only have OSPF running currently. So let's do router BGP 100, as we will be using iBGP peering between the leaves and the spines. So instead of configuring each neighbors individually, we can use the BGP listen range command on the spines. So let's go 10.0.0.0/24. Let's configure a peer group here. So let's say peer group leaf switch, and then remote AS would be 100. So let's go neighbor leaf switch as the peer group, and we will use loopback 0 as the update source IP, and these leaf switches will be root reflector clients. And like we did on the leaf switches, we also need to enable the send community extended command to send extended communities and specifically the root target values. And like we did on the spines, we need to go under address family EVPN and enable address family EVPN against these neighbors. So we go neighbor leaf switch activate. So like we discussed in the theory section, when we enable the address family EVPN against an existing neighbor, the neighborship will be reset. So it is something that you might want to consider before you enable address family EVPN against existing neighbors, because there will be a reset of neighbors and you will lose traffic forwarding. So you might want to do it in a maintenance window. So if we check the BGP config again on Arista 5. So let's go show run section router. So we see we have configured BGP on Arista 5. We can copy and paste the same on Arista 6. So let's check the peering. So let's do show BGP EVPN summary. So we now have BGP EVPN peering with both Arista 5 and Arista 6. So now we will advertise the routes inside BGP. So we will have to define what routes, i.e. what MAC address and IP prefixes we want to be advertised within BGP. And we do that under router BGP mode. So we say router BGP 100. Then we define the VLAN that we want to be advertised inside BGP. So in our example, we have configured VLAN 10 and we have hosts in VLAN 10 across two different leaf switches. So we will advertise VLAN 10 inside router BGP, and we also need to define the route distinguisher value. So let's define a route distinguisher value of 10 colon 100,010. So we also need to define the route target value. So we can specify import export separately, or using the both keyword, we can define import and export values at the same time. So let's use the same value as we used for route distinguisher, that is 10 colon 100,010. And then we need to redistribute the learned routes. So that's all we need to advertise the MAC address under VLAN 10, and we would do the same for IP prefixes. So we will go under VRF customer A. So we will define a route distinguisher value. So for VRF A, let's give it a route distinguisher value of 100 colon 100,001. We then configure the route target under the VRF. So we go to router BGP, VRF customer A, and then the command is root target import EVPN and then the root target value. So in our example, root target value we are configuring is 100:100,001. Likewise, for export EVPN root target, we will be using the same value. And then we redistribute the connected routes inside BGP. So the command is redistribute connected. And that's pretty much it. So let's check the running config inside BGP. So we have router BGP, VRF customer A. We defined the route distinguisher for VRF customer A, and then we also defined the import and the export root target. So we can remove this command, which is root target import 100:100,001, because this command has been deprecated. So let's do a no to this command. Like we see, when we enable this command, we got this error message or warning, even though it took this configuration, but the recommended way to define root target is to use the EVPN keyword and then the root target value. And we will apply the same command on the other Arista leaf switches. So we will say router BGP 100 VLAN 10, the root distinguisher and the root target values, along with the redistribute learn command. Then we also add the VRF customer A. So this was done on Arista 2 already. So now we will apply that config to advertise the MAC and IP routes on Arista 3. So we will go router BGP 100 VLAN 10 and then the route distinguisher and the route target values for VLAN 10. And then we also define the redistribute learned command. And then we will go to VRF customer A and then define the route distinguisher and the route target values along with the redistribute connected command. So let's check Arista 4 now. So let's do a show run section router. Yep, the command has not been defined. So let's go router BGP 100 VLAN 10 and under the VRF customer A we define the route distinguisher and the route target along with the redistribute connected commands. So that's all done. So now on Arista 1, let's check if we have started learning any prefixes via BGP EVPN peering. So let's do a show BGP EVPN summary. Yep, we are receiving 4 prefixes from the spines. So now that we're learning the prefixes from the remote VTEPs, let's run some tests between our client devices, which are switch 1 and switch 3. So let's check the IP address configuration on switch 1 first. So it's show IP interface brief, exclude the UNA. So it has an SVI for VLAN 10 with an IP of 192.168.10.10. And likewise, switch 3 has an SVI for VLAN 10 with an IP of 192.168.10.30. So let's go to switch 1 and ping 192.168.10.30. Yep, we do have reachability between these devices. So let's check ping request between switch 1 and switch 3. So let's open up this packet. We see that this is an echo request with a source IP of 192.168.10.10 and a destination IP of 192.168.10.30. This packet has been VXLAN encapsulated with a value of 100,010. So that's the VLAN to VNI mapping that we configured under the VXLAN tunnel interface. And like we see, the UDP port that VXLAN encapsulation uses is port 4789. That's what we saw on the interface VXLAN 1 on our Arista devices. And we also have the outer source IP of 10.0.0.2. That's the loopback 0 IP on Arista 2. And then we have the destination as Arista 4, and this is the loopback 0 IP configured on Arista 4, which is also the source IP of the VXLAN tunnel interface. And now if we have a look at the BGP EVPN table on Arista 4, we'll see that we're learning the MAC and IP route for the SVI on switch 1 from both Arista 5 and Arista 6. And this is expected as Arista 5 and Arista 6 are the two root reflectors in our topology. So Arista 4 will be learning any remote MAC or MAC and IP prefixes from both the two root reflectors. So that's what we saw in the BGP output on Arista 4. So what's going to happen is that for all the MACs or MAC and IP routes that gets advertised from switch 1 towards Arista 1 and Arista 2, those MACs or MAC and IPs will be advertised via BGP EVPN towards the spines from both Arista 1 and Arista 2, and the root reflectors, i.e. Arista 5 and Arista 6, will advertise those prefixes towards the other leaves, for example, Arista 4 in our topology. And Arista 4 will make the forwarding decision based on the BGP best path selection, which will lead to traffic polarization, because either Arista 1 or Arista 2 will be selected as the next stop for those advertised MACs or MAC and IP prefixes, and again, which will lead to traffic polarization. To work around this issue, we will be configuring a shared anycast IP on both Arista 1 and Arista 2, and we will be sourcing the VXLAN tunnel interface from this shared anycast IP. And in our topology, we will be using an IP of 10.0.0.12 on both Arista 1 and Arista 2. So the VXLAN tunnel interface will be sourced from this IP. However, the BGP session will still be sourced from loopback 0 of the individual Aristas, i.e. Arista 1 and Arista 2. So let's go to Arista 1 and configure loopback 1. Let's give it an IP of 10.0.0.12/32, and also let's advertise this IP in our IGP, which is OSPF in our topology. So we go IP OSPF area 0, and let's do the same on Arista 2. Let's configure interface loopback 1. IP address is 10.0.0.12/32, IP OSPF area 0. So now the OSPF neighbors of Arista 1 and Arista 2 should be learning this loopback IP of 10.0.0.12 from both Arista 1 and Arista 2. So let's take a look at the OSPF routing table on Arista 5. So let's go show IP route OSPF. So we are learning 10.0.0.12 from both Ethernet 1 and Ethernet 2, and Ethernet 1 is connected to Arista 1 and Ethernet 2 is connected to Arista 2. So like we discussed, the anycast IP of 10.0.0.12/32 is getting learned on both Ethernet 1 and Ethernet 2 from Arista 1 and Arista 2 respectively. Now on Arista 1 and Arista 2, we will change the VXLAN tunnel source interface to loopback 1 instead of loopback 0. So let's check the current configuration of interface VXLAN 1. So we are using the source interface of loopback 0. So let's change that now. So we go interface VXLAN 1. We will shut it down before we change the source interface. So let's go no VXLAN source interface loopback 0, VXLAN source interface loopback 1, and let's do a no shut. And let's check the show interface VXLAN 1. Interface is now up. So let's do the same on Arista 2. So let's go interface VXLAN 1. Let's shut it down. And then we say no VXLAN source interface loopback 0. VXLAN source interface loopback 1, and let's do a no shut. Let's verify the interface VXLAN 1 has come back up. So yeah, the VXLAN tunnel interface is back up. So let's push some traffic from our end hosts, which are switch 1 and switch 3. So let's say ping 192.168.10.30, which is the SVI IP of VLAN 10 on switch 3. So yeah, the pings are still reachable. So let's check the BGP table on Arista 4. So we are now learning the SVI MAC and IP on switch 1 from the Anycast IP that we configured, which is 10.00.12. So let's check the BGP entry on Arista 4 for this MAC and IP prefix. So we go show BGP EVPN root type MAC and IP. So let's check for this MAC and let's do a detailed version of the same. So we see that we are learning the MAC address from both the root reflectors, i.e. Arista 5 and Arista 6, and the remote VTEP is 10.00.12, which is the shared Anycast IP on both Arista 1 and Arista 2. So this way, traffic for any device behind Arista 1 and Arista 2 will be load balanced to both Arista 1 and Arista 2. So previously, traffic was getting polarized to either Arista 1 or Arista 2. So now, any traffic that hits Arista 5 or Arista 6 with an outer destination IP of 10.0.0.12 will be load balanced to Arista 1 and Arista 2. So that's the reason we configure the shared Anycast IP on Arista 1 and Arista 2 and use that shared IP as the source of the VXLAN tunnel interface. So friends, this was a detailed explanation and implementation of VXLAN with BGP EVPN on Arista EOS platform. I hope you like the content of this video, and if you do like the content, please give it a thumbs up. Please leave your comment in the comment section. And if you haven't subscribed to my channel yet, please consider subscribing. And please share this video with your friends or colleagues who might find this video helpful. And so thank you very much for your time today, and see you in future videos. Thank you.